So Chris is a second-year grad student under Juan Pablo, and I've had the pleasure to work with him on Pajarito, and he's going to talk about a lot of work that we've done. This work came out of work that started at Los Alamos, and Chris has picked it up and rewritten it all from scratch multiple times. And we'll hear a bit about that now.
I think that wasn't the. I was reading the software engineering plan that at some point we came up with looking at it with Yiho about Julia and Jump, and that actually was there by design. It's like you write it, you realize that it doesn't work, you rewrite it, and you just iterate. So it's exactly it's by you can now say that it's by design.
Cool. Okay. Welcome, everyone. I think it's going to be a high of 94 today. So, yeah, Boston weather for you.
What's that in Celsius?
Celsius. You picked up on the accent. Okay. I'm originally Australian. Celsius. I can convert between like the 60s and 70s, but I don't.
35.
35? Okay, body temperature is about 37, 98. So yeah, that sounds about right. Okay, so I'm going to be talking about Pajarito Solver. Pajarito is a solver for mixed integer convex optimization, which I'll define. So originally Pajarito was written by Emery and Miles and Russell Bent at Los Alamos, and it's named after a mountain in Los Alamos. And then more recently, I've been working on it with Miles and Juan Pablo, in particular on the Conic algorithm, rather than the nonlinear NLP algorithm. So this presentation is going to focus a little more on the Conic side of things, actually a lot more on the Conic side of things. But at the end, I'm going to give you time for questions, and probably Miles would be able to answer the NLP questions better than me. So I'm going to define the problem. I'm going to give you some algorithmic background. Then I'm going to discuss the architecture of Pajarito. Then I'm going to discuss very briefly, as Miles has already mentioned, these potential changes that we're going to discuss this afternoon, and they will probably affect Pajarito quite significantly. So I'll discuss that. And then if we have time, I'm going to do sort of an interactive look at some of the important parts of the code. And you guys should ask me questions, interrupt me, etc., especially in that point. I'm going to move quickly through the algorithmic stuff. Okay, so mixed integer convex optimization, also known as convex MINLP. These are problems that are convex except for integrality constraints on variables. So this generalizes both convex optimization and mixed integer linear optimization. Ooh, that's not good. Sorry, I'm having issues. All right, let's try that. Ah! Does anyone know how to use Adobe Reader? Single page view. Yeah? Full screen. Is that full screen?
No.
Is this full screen?
Try Control L.
Control L.
Yeah.
Okay, thank you. Right, so and many useful non-convex sets can be modeled in this way. So with convex optimization, we could model this sort of convex hull of these two sets, but with mixed integer convex optimization, we could actually model the union of those two sets rather than just their convex hull. So here's a general form for mixed integer convex. We might write it with a linear objective, some set constraint here, where S is a convex set, and then we have integrality constraints down here on a subset of the variables. A bunch of applications, won't go through these, but these slides will be available so you could have a look. So how can we solve mixed integer convex optimization? Well, polyhedral approximation leverages the power of MILP solvers, such as Skip, Gurobi, Cplex, etc. These are mature, they're powerful, they're numerically stable, and this enables reliable cutting plane algorithms. So here's a very dumb kind of algorithm. So let's say this blue set here is S. So that's the actual feasible region. And we're going to use a polyhedral outer approximation defined by everything under these initial sort of cuts, these red lines. Let's say we solve that outer approximation model and get this X star. Then we might want to add this cutting plane here with the dots to cut him off and get us closer to the set S. Okay, very briefly, that's a naive algorithm. We can improve it by using extended formulations. And Miles, in a paper last year, and collaborators looked at using disciplined convex programming to automate conic extended formulations for these problems. And that allows us to greatly accelerate outer approximation. And I won't go into the theory of that, but Miles and collaborators found that all 333 of the convex mixed integer problems in the MINLP-lib2 library can be encoded with about 5 cone types. And in an upcoming paper, we're going to detail a conic framework and the conic algorithm from Pajarito and test that out on example problems and show it as the fastest mixed integer convex solver. Okay, so a little more about the algorithm. As I said, I'm going to move quickly through this part. So we saw a mixed integer convex form, and this is mixed integer conic form. So here we're saying a fine expression is in a convex closed cone, and there's k of those constraints. Some of them may be the LP cones, like the non-negative orthant, and some may be cones such as the second order cone or the positive semi-definite cone, non-polyhedral cones. Okay, so we're just going to assume that our problem is feasible, and if it's feasible, then its optimal value is attained. So we're going to write min and max instead of inf and sup. Okay. So I'm going to define what a dual cone is, and that's going to help us see how to do outer approximation with cones. So a dual cone of a closed convex cone is all of these vectors such that the inner product with any vector in the cone is non-negative. So we can reformulate one of those non-polyhedral conic constraints, k, as an infinite number of linear constraints. So linear is good because we want to use an MILP solver. Infinite is not good because these solvers are not semi-infinite solvers. But it's a step in the right direction. And then instead of using all of those, we're instead just going to pick a finite subset of points from the dual cone and impose the linear constraints that correspond to that finite subset. So now we get an MILP relaxation of our mixed integer conic problem. And we're going to call these cuts k-star cuts because they're sort of derived from the dual cones CK, but K is sort of more a generic name. Okay, so these cuts are not unique, but we're going to choose a particularly good way of finding them. To do that, we're going to solve conic subproblems, continuous conic subproblems, using conic solvers. This will yield an algorithm that has finite convergence guarantees under some reasonable assumptions. So let me just define these problems. We have the original MICP, which is conic here, not convex. And we have this MILP outer approximation model that we're going to refine iteratively. We have the continuous conic relaxation of M, which is just removing the integer constraints. And then here is a version of this where we are restricting the integer variables to their values in some solution X. Okay, so the geometric intuition goes as follows. So consider this left part of the diagram here. Again, the blue convex region is the feasible set of M. Well, the blue convex region intersected with these integer sort of lines here. So this variable is integer, this one's continuous. Okay, so we're going to solve the relaxation problem, and we're going to get some dual or some k star cut, z bar, and we're going to add this cut to our MILP relaxation, and then everything under this is going to be feasible. Well, everything under this intersected with the purple lines is going to be feasible for our MILP relaxation, the outer approximation model, funky P. Now over here, this is 2 steps of this little algorithm. We're going to solve that MILP outer approximation and get this maybe this x star up here, okay? Then we're going to solve this continuous conic problem where we fix the integer values to this value, the purple line here. And the dual on that is going to give us a cut that might look like this. And it's tangent right at that point, which is nice. We're going to add him, and if this is feasible, in this case it is, then we're going to check if the new solution, x bar, which is going to be here, is a new incumbent for our MICP problem. Update our upper bound. And then we're just doing the exact same thing here again, except we got this solution, x star here, and we're going to fix this integer value and solve this subproblem, get this dual and this cut here. So that's the intuition behind it. So this is what conic duality looks like. This is Boyd and Vandenberg, their convex optimization book. They're really in favor of this conic representation thing. This is a very mechanical transformation, and it's very much just a generalization of LP duality. So these guys are like duals on these constraints, and sort of the 0 cone is dual to the free cone. So it's very simple, very elegant duality there. I'm not going to go through this due to lack of time, but we'll try and get these slides up. This is just how these cuts work. We come up with a bunch of algorithmic extensions, which we detail in the upcoming paper and also implement in Pajarito Solver. So for example, because MIP solvers are not homogeneous solvers, they typically use absolute violation tolerances on constraints. We come up with a way to scale our k-star cuts that gives us certain guarantees. We internally manage a disaggregated extended formulation for the second order cone, which Juan Pablo and collaborators came up with, and which they showed greatly improves the speed of outer approximation algorithms for MISOCP. And soon after that paper was published, Cplex and Garobi implemented this very soon after. So we also do, for the positive semi-definite cone, extreme ray cuts. So we'll decompose a dual, which is rank k, into k linear cuts that are rank 1, giving us a stronger outer approximation. And in fact, if we use second order cone cuts for the positive semi-definite cone, based on this idea of the Scher complement or based on these scale diagonal dominance conditions, then we can actually solve an MISOCP outer approximation model, either using Pajarito in Pajarito or just using Cplex or Garobi's MISOCP functionality. And so it's not necessarily just polyhedral outer approximation. It could also be MISOCP outer approximation. Okay, so now architecture of Pajarito Solver. So Pajarito is open source, written in Julia, integrated with JuliaOpt, which Miles has discussed. It uses math-prog-base to accept mixed integer conic input from multiple modeling packages, and also to call MIP solvers and the continuous conic solvers in a solver-independent way. Currently, it supports the second order cone, the exponential cone, and the positive semi-definite cone, but the code is very simple and easy to extend. And we have many algorithmic options, including all of the ones I just mentioned on the previous slide.
Those are 30 individual options?
Yeah.
So you can combine, so it's like how many total algorithms?
Well, you can't combine all of them. It'll show you an informative error message if some options are just not compatible, but there are a lot that are compatible. Yeah. Okay. So I won't go through the computational results, but if you want to see them, we can talk later. They're in an appendix to these slides. What we found is that if we use Pajarito with Cplex's MILP solver and MOSEX's SOCP solver, then we can beat Cplex's specialized MISOCP solver. This is all using default, like Pajarito's defaults and Cplex's defaults. The only thing that's not default is that we use our single tree branch and cut rather than our iterative algorithm, which I'll describe. So, and we do change some tolerances on Cplex's MILP solver when we use them for Pajarito. So we also beat the open source solver BondMin very convincingly by using open source MIP and Conic solvers.